Hi everybody. Let's start where we finished off last time. So in the last lecture I started chapter 17, which is all about alcohols and phenols. And we're going to continue on that discussion today. Remember, this lecture is going to be 3 parts. And so today we're going to talk a little bit about kind of how to prepare alcohols. A lot of this is review, which is really good, right? We need a little bit of review. And then in the last part of the series, we're going to talk a bit about the reactions of alcohol. But I asked you to, work on this problem, kind of think it through, as we talked a lot about structure-property relationships, and I give you some data regarding boiling points of certain alcohols of, different constitutional isomers, and how would you account for the trend. So I've given you 1 butanol, and so the thing is, I was like, you should make sure that you draw the structures first. Anytime I ask you to rank something in terms of boiling point or in terms of acidity and basicity. So this is 2-butanol, and then this is 2-methyl-2-propanol. So these are constitutional isomers. And it appears that 1-butanol has the higher boiling point, and 2-methyl-2-propanol has the lowest melting point in this series. And the first thing you always want to look at is what? When you're thinking about ranking boiling points, you're thinking about intermolecular forces. Excellent. So we talked a lot about that. So the stronger the intermolecular force, what happens to the boiling point? It also increases. Excellent. So we know that, but you look at all these, and what is their most dominant intermolecular force for the 3 compounds? You would say hydrogen bonding, right? So that means that we really can't distinguish between the 3 of these based on intermolecular forces because they all participate in hydrogen bonding. But there may be some other factor that's affecting, the strength of that particular hydrogen bonding force. For example, it must be a lot stronger for 1-butanol, and that's why it has a higher boiling point than, for example, 2-methyl-2-propanol. And what do you think it is? Just looking at the structure. Hopefully you said sterics. Good. So, this looks very bulky here, right? And so there's these big methyl groups here. So when it starts to interact with another 2-methyl-2-propanol, do you think they're going to have as strong of hydrogen bonding interactions as you would say, for example, something like 1-butanol where 2 molecules are interacting? What do you notice here? That just by drawing it, we can draw 2 molecules a lot closer together. And so the trend that I wanted to point out with this learning check, sometimes you're like, you go straight to like intermolecular forces, but there's other things that play a role, and that's branching. Okay? So branching decreases the strength of the intermolecular force, which in turn decreases the boiling point, right? If your intermolecular forces are weakened, then the boiling point is also decreased. Because remember, boiling point is converting that molecule from a liquid to a vapor phase, so pulling them apart basically. So by weakening their intermolecular forces through branching, it's a lot easier to boil that particular molecule. Okay? So I just wanted to kind of point that out to you. Sometimes it's like the simplest answer, just look at the structure, and I always compare the 2 extremes, right? Because I think it's very easy, especially if you're given data, to compare the 2 extremes, and everything else kind of lines up in the middle. Okay? Now let's go into preparing alcohols. And like I said, this is a lot of review from chapter 8 and chapter 9, so it's going to be great for all of you to kind of review over some of that material. Those reactions were so critical. Remember, alcohols can be derived from a variety of compounds. Like we talked a lot about alkenes in chapter 8. So if you want to review over those lecture notes or that particular video or videos, that would be very advantageous for you. You can make them from carboxylic acids, ketones, aldehydes, and esters, and ethers and alkyl halides. You already know alkyl halides. We studied that in chapter 10. And so, and these are relatively easy. I'm going to talk about those today, the carbonyl groups. And then we'll definitely study a lot about carbonyls in chapters 19 through, I believe it's 23. So it's all carbonyl chemistry. So you'll get a lot. There'll be a lot more review here, but as we go into those deeper chapters, we'll study those mechanisms more. So just thinking back to chapter 8, the alkene chemistry, all the reactions of alkenes. Like, do you remember what are some ways to prepare alcohols from alkenes? Hopefully you said oxymercuration. And I'm going to show the reactions in later slides. So we won't draw the structures out yet or the reaction, but I'm going to show them in a few slides or in the next slide. So oxymercuration, we also had what else? Hydroboration, good. And those were to do just one alcohol, right? And we'll talk about the regiochemistry, Markovnikov versus non-Markovnikov. But how would you make a diol? How would you make, like, for example, a cis-1,2 diol? Hopefully you said osmonium tetraoxide. We always had to do the workup with sodium bisulfite. And if you wanted to do a trans-1,2 diol, you could start off with an epoxide, or you make an epoxide from an alkene, and then do an acid-catalyzed ring opening to make the trans-1,2 diol. And these are all, just kind of generically going through different ways you can prepare alcohols. And like I talked to you about in 12A, it's really important that you organize your reactions. And I always found it helpful as a student to organize my reactions based on functional group. So I had a list of reactions, like how do I prepare alcohols? These hydration reactions that we call them. And so I had a whole list and, changing up the starting materials or the reagents that I was using. And some of these reactions overlap, right? How do I prepare aldehydes? How do I prepare carboxylic acids? And so really, if you haven't done so already, I would start organizing those reactions now and see where the overlap occurs. And then that's going to help you to create that organic reaction roadmap, which is a fantastic extra credit project to do, because then, you get extra credit if you do a really good job, and it's going to help you organize all the reactions and connect them together. Because if you try to memorize the reactions linearly, it's never going to make sense. You need to see how everything is connected together. Okay? So if you feel rusty on this material, once I kind of review over it, because I'm going to go through it quickly, make the time to rewatch Chapter 8 lecture videos. That's probably one of the most important chapters from 12A, besides Chapter 11, right? SN1, SN2, 1 and 2. You really need to know those reactions because they're so critical to multi-step synthesis. So kind of reviewing over oxymercuration versus hydroboration. So remember that in hydroboration, we follow non-Markovnikov hydration. And so when I talk about Markovnikov or non-Markovnikov, I'm talking about regiochemistry. So both of these are regio-specific reactions, which means they're very particular about where that alcohol goes. And that really depends on the mechanism. And we went through a little bit of the mechanism of hydroboration. We talked about the intermediate, making this organoborane intermediate here. And the second step is always using hydrogen peroxide under basic conditions to oxidize that borane group into an OH. Now, something else that I wanted to point out is that this is also a stereospecific reaction. Just to remind you, it's stereospecific. And what I mean by that is that the BH3, when it goes and makes this intermediate, or, we were looking more on the transition state when I went through that lecture with you, you can see how the BH3 almost splits up, right? And it made what, in the transition state, what's proposed as a cyclic intermediate. And so the hydrogen on one side of the BH3 complex is on the same side as the rest of the borane molecule, the BH2. So this is what we refer to as syn stereochemistry. So a lot of times students get confused, like, well, syn with respect to what? We're referring to this BH3 complex. So knowing how to draw the intermediate is going to help you with stereochemistry for hydroboration reactions. Okay? And then once you've made this intermediate, like I said, oxidizing it under basic conditions replaces that boron group with an OH. And you notice how the OH is on the least substituted side of the double bond, and that's non-Markovnikov regiochemistry. Okay? Now, the other alternative, let's say I want Markovnikov regiochemistry, I want the alcohol on the more substituted side of the double bond, then the conditions you're going to choose is for oxymercuration, and that's where you react mercury diacetate in water. And then we have this mercury, you're going to make that mercurinium ion, and we're not going through the whole mechanism right now. Like I said, this is review, so if you need to review over those lecture notes, then please do so, and you should, to refresh your memory. But you can make the mercurinium ion, and then the sodium borohydride is a reducing agent. We're going to talk more about that today. Is a reducing agent that gets rid of that mercury. And then we have the methyl group, the OH group, on the Markovnikov or more substituted side of the double bond. Okay? Excellent. Cool. So make sure you review over those. They're going to be very important reactions. Useful for your multi-step synthesis. Okay. We also just talked about cis-1,2 diols. And remember, cis-1,2 diols are made from osmonium tetraoxide in the presence of a weak base like pyridine. And it makes this cyclic osmate intermediate. And so we didn't go through the full mechanism of this, but we did talk about the intermediate. And if you know the intermediate, then you understand the stereochemistry. Once again, it's a stereospecific reaction, so you're only going to get one product. Like I said, this is cis-1,2 diol. And the reason for that is because it's a cyclic intermediate. And so once the sodium bisulfite comes in and reduces that bond, gets rid of the osmium, then you have that cis-1,2 diol. The alcohols are still on the same side, kind of reflecting what you saw in the intermediate before. Okay. However, if you wanted a trans-1,2 diol, this is once again a stereospecific reaction, then you would need to react the alkene with some type of peroxy acid. And the common one we talked about was MCPBA. You need to know that acronym, you need to know what it stands for. It stands for metachloroperoxybenzoic acid. Okay, so that's a great peroxy acid, but on the ACS exam they may give you other types of peroxy acids. Just remember CO3H stands for that peroxy acid. So it looks like a carboxylic acid, but it has a peroxide bond in it. That's where the 3 oxygens come from. Okay, methylene chloride's just a solvent here, and this is how you make an epoxide from an alkene. Very useful reaction. We're going to talk a little bit more about it in Chapter 18 as well when we talk about ethers and epoxides and that sort of thing. But in order to open it up and make the trans-1,2 diol, we need to add acid. And this is going to be an acid-catalyzed reaction. And I challenge you to go back to your lecture notes and look at the mechanism for that. Don't have time for that today. It's already recorded, like I said, in Chapter 8. Look back at that chapter and look at that mechanism and see if you can derive it yourself, because you're going to see a lot of acid catalyzed mechanisms very near in your future, and the carbonyl chemistry when we get to it. Okay, so it's an acid catalyzed reaction. It opens up the ring, and we end up with a trans-1,2 diol, stereospecific reaction. Now, I want to point out here, they do give the names, and they talk about this in your textbook, and it's really interesting to read through it. I'm not going to test you on using this kind of nomenclature here. All I ask you is if you have a chiral center like this, you can just use R or S stereochemistry. That's all I'm going to focus on. This kind of nomenclature is a little bit more advanced. I didn't want you to see it in the textbook or see it on my slides and just be like, what is going on here? But it is a way for us to name cycloalkanes, and especially with their stereochemistry. You know, you're talking about some reference here, and if it's trans or cis, so, but don't worry about that. Like I said, if you do RS stereochemistry for chiral centers, you will be safe. Okay. So let's just practice, you know, let's predict the products of the following reactions. Pause the video and then come back and check your work. Good, hopefully you've had a chance to work on this. I noticed that the key functional group I have here is an alkene. You'll notice when I talk about in work sessions and, you know, anytime I approach a problem, a predicting products problem or multi-step synthesis, I look for the reactive functional group and I use a highlighter. I don't have a highlighter here, but I have, you know, I'll circle it and say, okay, that's the only thing that's going to react with anything, right? These cyclopentyl groups are just white noise, right? It just makes it bulky and a little scarier looking, but doesn't contribute to the actual reactivity of the molecule. And then I look over here, I see osmium, osmium tetraoxide and pyridine, sodium bisulfite, and water, and that looks very similar to what we just talked about. I know that this is some type of oxidation, hydroxylation reaction to make a cis-1,2-diol. And so I want to represent that. If it's stereospecific, I want to show that stereochemistry and indicated in my molecule that I'm forming. And so the OHs are going to be on the same side. And there you go. Right? The next one, once again, the only reactive functional group we have to work with is a double bond. There's nothing else there to worry about. Everything else is white noise. And so we're doing mercury diacetate and water with a reductive workup with sodium borohydride. This is going to be your oxymercuration. Okay? Oxymercuration gives us what type of regiochemistry? Markovnikov. Now, is it a stereospecific reaction? Not really. So we don't have to worry about it, especially because we're not making a chiral center here. You just want to put the OH on the more substituted side of the double bond. Now, you'll probably hear me talking as I'm lecturing and everything, talking you through this. And I like to use the names of the reactions a lot because I always want you to be able to know the name of the reaction because it helps you to, you know, for the most part, I feel like it helps you to remember what kind of product you're going to get from it. So it's really important that you do know the names of reactions like oxymercuration or hydroboration or, let's see, well, you know, any of those kinds of reactions, you know, just making alkyl halides and that sort of thing, or halohydrin formation. It's just important to know the names so that it kind of gives you clues as to what type of product you're going to get. Okay? So like I said, a bit of review, study over Chapter 8, review over that material. And the ACS study guide, there's a chapter on electrophilic addition. It's also a great way to see where you feel weak at in those particular reactions. Okay. Now I said that we can make alcohols from carbonyl compounds, and in doing so we can make them by reducing carbonyl compounds. And this is the most general method for preparing alcohols. Okay, and this is the most general method. So you're going to use it a lot, especially in your multi-step synthesis. You know, you get to a carbonyl and you just want to end up with an alcohol functionality in the end. You're going to do some sort of reduction step. Okay, very easy to do. It's also very common not only in the laboratory, but in living organisms. So if you take biochemistry, cellular and molecular biology, you're probably going to see a lot of these reducing reactions. Now, using different types of reducing agents, much larger reducing agents, but nevertheless, still a type of reduction. Okay? And if we do have an organic reduction reaction, it adds an equivalent of a hydrogen to a molecule. And I'm just talking about a normal aldehyde or ketone. You notice here in the brackets, that just means reducing agent. I'm going to talk about what types of reducing agents you can use here. But you can see here that we've pretty much added an equivalent of hydrogen, H2, right? And so that's a reducing or reduction type reaction. And anytime you add more hydrogen, you're decreasing, you're gaining electron density at that carbon center. Remember the difference between oxidation and reduction reactions in organic. Reduction is a gain of electron density at the carbon center. So for example, you're like, okay, well, how do I know? Well, this one, definitely carbon's partial positive, and this is partial negative. It's that oxygen's way more electronegative, so it's pulling a lot of the electron density towards itself. However, by adding hydrogen here, which is not as electronegative as carbon, the partial positive charge decreases. You still have an oxygen there, which is partial negative, but you can see that carbon has gained some electron density back by doing this reduction reaction. Okay? If you ever forget, remember the acronym oil rig. Oxidation is a loss of electron density. Reduction is a gain of electron density. You learned that probably back in general chemistry, but now we're really focusing just on carbon, right? It's still the same premise, right? But just focusing on carbon. Now, reduction of aldehydes and ketones, and we'll get into aldehydes and ketones in way more detail in chapter 19. But aldehydes end up producing primary alcohols, and ketones end up producing secondary, my apologies. Aldehydes end up producing primary alcohols, and ketones end up producing secondary alcohols. It's really important you know the substitution patterns. Remember that we name a primary alcohol primary because it's attached to a primary carbon. That carbon only has one other R group attached to it, right? Whereas a ketone, when you reduce it, it makes a secondary alcohol because the carbon attached to it only has two R groups attached to it. So it's the substitution of the alcohols based on the carbon it's attached to. Now, what types of reducing agents can you use? Sodium borohydride is not sensitive to moisture, and it does not reduce other common functional groups. I'll get to that. Sodium borohydride is going to be your safest option for aldehydes and ketones, because you may be in the presence of water in your reaction, and because it's not sensitive to moisture, it means it's safer to work with. Whereas the more powerful reducing agent is lithium aluminum hydride, and it is powerful, and it's less specific. It'll reduce, carboxylic acids and esters and other groups, but it's very reactive with water, so you have to be really careful when you're working with it in the laboratory. So if you're working with aldehydes and ketones, I suggest that you use sodium borohydride rather than lithium aluminum hydride. But I just want to point out that lithium aluminum hydride will work as well. It's just, I want you to think like a chemist and, act as though you are actually performing this particular experiment in the lab. You're always going to want to choose the safest option. So start developing that chemical intuition, right? Once again, it both adds an equivalent of hydrogen to it, and more specifically it adds a hydride, and I'm going to go over that in the next slide, kind of a generic, very simplified mechanism. But remember, H minus means hydrogen with a lone pair, so has a negative one formal charge. That's going to act as your nucleophile when it reacts with your aldehyde and ketone on the first step of the reduction. Okay? Now, another thing I want to point out, make sure you highlight it and you don't forget it, because so many students do. You don't want to be that student, right? The first step in reductions is always add the reducing agent. The second step is to acidify, to add acid to help neutralize the intermediates. You need this step, and you don't want to forget it. You're going to see why in the next slide when we talk about the generic kind of simplified mechanism for it. So make sure you add acid in the second step. You don't want to add them at the same time. If you write sodium borohydride and acid and no numbering, then you're saying, I'm adding at the same time, it's not going to work. The sodium borohydride is going to react with the acid as opposed to your aldehyde or ketone. You need it in 2 separate steps. You run the reaction, and then you work it up under acidic conditions. Okay? Very important that you do that. I will take off points off your multi-step synthesis or predicting products, or whatever it is that you're working on. I know you may be thinking, wow, that is really picky, Dr. P, but once again, I'm trying to train you to think like a scientist and what you would have to do in the laboratory. You need to know in what order to add reagents and at what time. Okay? So you don't add the acid at the same time as sodium borohydride. That will ruin your reaction. So I wanted to briefly go over the mechanism of reduction. I'm going to I'm going to talk about it again in chapter 19 when we talk about aldehyde and ketone chemistry, and so which will be nucleophilic addition. So basically what happens is that this hydride is attracted to this carbonyl carbon because it's partial positive, right? These have lone pairs. It tacks, pushes those electrons up top, and this is called an alkoxide ion intermediate. You're going to see them all the time when we get to that chapter. This is the conjugate base of an alcohol, right? So this is the conjugate base of an alcohol, and that's the reason why we have to use acid in the second step, to help protonate the alkoxide ion intermediate and convert it into the alcohol functionality, which is what we desire. Okay, so this lone pair pulls off a proton off of the hydronium ion. These electrons go here, you just make water, right? And we've neutralized that intermediate to make the alcohol. So this will be eventually what you're going to learn in chapter 19 called nucleophilic addition. And basically what is happening is that the hydride anion attacks the electrophilic carbon atom of the carbonyl group. Okay? And then once again, like I said, I can't emphasize this enough because I see students miss it all the time. But the second step in reductions is to add acid to neutralize the intermediate. And I always get students, talking to me like, Dr. P, there's so many reagents to learn. It can be quite confusing, and it's just a lot, right? And I always tell them, don't memorize. If you actually understand a mechanism, or maybe a simplified version of a mechanism, because, like I said, this is overly simplified. I'm not telling you how the sodium borohydride complexes and helps with the reduction. Just focusing on the basics here. And if you understand just a basic mechanism, then you'd understand, okay, I know I have an alkoxide ion intermediate. I need to add something to that in order to make the alcohol. So really think it through and know your mechanisms so that when you do get to an exam, you get a little overwhelmed because you see all these, different structures and you're just like, oh, I know what reaction this is, but I need to remember the reagents. Maybe try your best to think about the mechanism itself. And seeing this would hopefully, click on that light bulb that says, yes, aha, I need to add acid, right? That's my second reagent. I know I needed it. I know she said it over and over in her lecture slides. Don't make that mistake, okay? Now, I'm just talking really more specifically about aldehydes and ketones, but what about carboxylic acids and esters? You can reduce those two into alcohols. However, sodium borohydride is not going to be very effective. It will give you very low yields. So we really need to use lithium aluminum hydride. Even though it's not as safe, you just have to be really careful when you're working with it. And both carboxylic acids and esters reduce to give primary alcohols. Okay? And this will be something we will discuss way more into chapter 21 when we talk about nucleophilic acyl substitution and all the carboxylic acid reactions and mechanisms and things like that. So I don't really want to go through the mechanism too much now. I just wanted to point out to you that you can reduce it down into a primary alcohol for both, right? And we'll explain why later how that's kind of this simple alcohol is, acting as a leaving group in a sense. You'll understand in great detail when we get to chapter 21. Okay, but just understand that when we reduce carboxylic acids and esters, first of all, they give primary alcohols, and we need to use lithium aluminum hydride and then acid as a workup in order to do that reduction. Another way to make an alcohol is to do a Grignard reaction. This is one of my favorite reactions. I did this reaction so many times in undergrad for my research, and you'll actually get to be able to do a Grignard reaction yourself. And so it's always really interesting. It takes really good technique. You have to be really careful when you do these Grignard reactions, but usually my students end up doing very well. And we talked a little bit about Grignard reactions back in chapter 10. I did talk about the formation of a Grignard reagent then. And then we did a very basic Grignard reaction. We didn't react it with a carbonyl. And so it was just very simple, very basic reaction. But in this case, this type of Grignard is going to be way better because it's going to be giving us a carbon-carbon bond. So it's one of those carbon-carbon bonding formation reactions. And I always told you back in 12A, and I'll tell you again in 12B, that if you want to win a Nobel Prize in organic chemistry, you develop a new carbon-carbon bonding formation reaction that's never been discovered before, that's highly efficient and easy to do, and then you can name it after yourself, right? So they're very few and far between. So this is going to be one of those really important reactions you stick in your mind like, yes, I need that for later. Right up until now, all we've done is sodium amide coupling, chapter 9, so with triple bonds. So other ones that we talked about in chapter 9, sodium amide coupling. And we also talked about chapter 10, the Gilman, which is another very important carbon-carbon bonding formation reaction. We did talk about Grignard, but like I said, we just did kind of a very basic Grignard. It just gave you a hydrocarbon. It wasn't anything special. You can review over it, and I challenge you to review over that and just to see the difference between the two. And then in chapter 16, you learned about Friedel-Crafts, alkylation and acylation, more specific to aromatic substrates, right? But still carbon-carbon bonding formation. So really important reactions. We'll learn more as we keep going. But like I said, the Grignard is going to be one of those really important ones that we do. Okay? So in order to do a Grignard, you have to make a Grignard reagent. The ingredients for that, you need an alkyl halide, and you can use alkyl. I say alkyl, but you can use aryl, so aromatic halides or vanillic halides. There's no kind of limitation to that. And then you react it with magnesium metal. So when we actually do the reaction, we're going to dry the magnesium metal in the oven, make sure it's clean and shiny. And the magnesium inserts itself in between the bond that's between the halogen and the rest of the group. Right? That's your Grignard reagent. And what's really interesting about Grignard reagents is that they have a nucleophilic carbon atom. You see this carbon atom here is partial negative, and the magnesium's partial positive. It's a metal, right? And so, so that's going to be your Grignard reagent. So you have a nucleophilic carbon. We're so used to carbon being partial positive, right? Especially like this one here, because it's attached to an oxygen, right? So what ends up happening in these particular mechanisms is that the nucleophile attacks the electrophile. These electrons go up onto the oxygen. Remember, originally it had 2 lone pairs. You're going to make a very similar intermediate you've already seen before. you're going to make an alkoxide anion intermediate. And I'm talking, this is once again more specifically to ketones and aldehydes. Right? And then what is the second step for a Grignard? Just like with reductions, we have to add acid. Why do we need to add acid? To help protonate the alkoxide ion intermediate and make the alcohol. Right? And don't worry too much. We do end up with a lot of salts here. You work it up during your extraction phase. It's very easy to deal with. I'm mainly concerned about the organic product here. You'll notice you have a carbon-carbon bond here. So this bond here can really make your molecule bigger. It's really exciting to go from something small and to grow it, right, into something more elaborate, maybe something more useful. Make sure I show the mechanism here so you can see it. The arrow comes here and the electrons come here, so you lose water in the end. But very similar mechanism to reduction, right, which will make your lives a lot easier. Once again, I'm not really showing you how the magnesium participates. If you take a more advanced organic chemistry class, you definitely will go into those nitty-gritty details. My goal right now is just to kind of simplify it for you so you understand the basics of the electron flow, so you're not overwhelmed, but you're also not just memorizing it, okay? You can see here a bunch of different examples. For example, we have, this will be partial negative, and this is partial positive, and partial negative. I mean, I still do that, you know, when I predict products and things like that, because I want to make sure that I have the nucleophile attacking the electrophile, and that I'm not adding carbons or losing carbons. So my trick for you to here is to number your carbons. So carbon 1 and carbon 2, where the new bond will be formed. We know that the nucleophile will attack the electrophile and push those electrons up top. I'm not going to go through the whole mechanism and show you the intermediate, but you can practice that, and we'll practice it more too later on when we get back to those chapters. But if you draw what you see here, you can say this is carbon 1, this is carbon 2. Carbon 1 just has the rest of the cyclohexane hanging off of it. Carbon 2 has 2 hydrogens, and this carbonyl eventually turns into an alcohol from the alkoxide ion intermediate. Okay. Ether is your solvent. Alternatively, sometimes you see them use THF as another solvent, and it just needs to be dry. It can have no water present. Absolutely no water present during the reaction. That's absolutely critical. No water present during the reaction here. Okay? I challenge you to do the same kind of numbering and formation of the new bond and see if you can predict the products of these structures. Very similar mechanisms. Like I said, we'll go into more detail in chapter 19, but you need to start learning this now. Okay? So just practice with the examples that are provided on this slide. Just some arrow pushing and the numbering. The numbering is going to help you a lot. Eventually we're going to have condensation reactions. You have 2 big starting materials. You have to glue them together. And my students love to number where the new bonds form because they'll be like, okay, what's hanging off of number 1? Just the rest of the molecule. What's hanging off of number 2? Just the rest of the molecule. Okay, the new bond's here. All right? That way you don't lose carbons or put too many carbons in. You just always are counting your carbons so you're not losing any or gaining any. Okay? You can do reactions of esters with Grignard reagents. Now I just want to point out that you will need 2 equivalents. Once again, we're going to study this more in chapter 21 when I get into that kind of mechanism. I don't want to go into that right now. It's a little easier to show you ketones and aldehydes right now, but it takes a little bit more time to show you a mechanism for the carboxylic acid derivatives. So I don't want to confuse you too much there. But what's interesting is that you must have 2 equivalents because it wants to keep reacting. We can't stop the reaction after 1 equivalent. So we had 2 equivalents to push the yield, and you'll get a tertiary alcohol, right? That's a typo. You'll get a tertiary alcohol, I promise you, right? You can see that because this carbon has 3 R groups attached to it. Okay. Now, what I want to point out is that you cannot do Grignards with carboxylic acids. It's never going to happen. And the reason why that is kind of comes back to chapter 10. There's an acidic proton there. And let's say, for example, I react it with methyl magnesium bromide. Now, that methyl group is a good nucleophile, but it's also a good base. So instead of reacting with the carbonyl carbon, it's just going to pull off the acidic proton, push those electrons onto here, and you're going to make your salt plus methane, which is not exciting, right? Very similar to what we saw in chapter 10 when we did a Grignard back then. And so not a useful reaction, and this is the reason why you can't react with water. You must have no acidic protons around. Otherwise, the Grignard is going to react with an acidic proton rather than doing attack at the carbonyl carbon. Okay? Make sure that soaks in. Makes sense. You don't want to do an acid-base reaction. Not in this case, right? There are some limitations that you need to learn for Grignard reactions. Now, this hopefully will make sense. If I have a reactive functional group, especially those proton donors, in the presence of a Grignard reagent, it's never going to work. So you never want to see carboxylic acids or thiols or amines or alcohols present because these all have acidic protons. In addition, if your Grignard reagent contains a carbonyl compound or some type of pi bonding, it may start to react with itself rather than the carbonyl or other pi bonding functional group you want to react it with. Okay? So you don't want to include a reactive functional group in your Grignard reagent. Okay? Because otherwise it starts reacting with yourself and then you'll get a mixture of products. Okay? So these are limitations. You want to learn them. Very critical that you understand that. Like I said, and I'm kind of showing you this already, the mechanism or the simplified mechanism is very similar to the simplified mechanism of reduction reactions. Grignard reagents act as nucleophilic carbon anions, and they add to the partial positive charge carbonyl group, like you've seen before. It makes an alkoxide ion intermediate, and then we have to acidify it to neutralize alkoxide and make the alcohol. Okay? So let's go ahead and practice what we just learned, and make sure you stop the video, try to predict the product or products of the following reactions, and then check your work. Good. Hopefully you've had a chance to do this already. So the first one, you see magnesium bromide, you're just like, okay, I know it's a Grignard. I know that this is the partial negative, so I'll make this carbon 1. It's going to attack carbon number 2 because this is partial positive. I'm not going to go through the whole mechanism, but I always find it useful to at least draw the arrows to get you started. And you have a new bond between carbon 1 and carbon 2. Okay? What is it else that you have? You have what's hanging off of number 1. You have a cyclohexane. Good. And what's hanging off of carbon 2? You have 2 methyl groups, and this eventually turns into an alcohol. Okay, so you just see how I kind of pieced that all together, kind of really simplified it? Okay. We'll keep practicing that. The next one, I see lithium aluminum hydride. I see that my reactive functional group is a carboxylic acid, and I have acid-acidic workup. It's definitely a reduction. Remember, carboxylic acids are reduced into what type of alcohols? Primary alcohols. Good. So it takes it all the way down to a primary alcohol. Be careful, count your carbons. I notice I have an aromatic ring here plus another carbon. Aromatic ring here plus another carbon. Sometimes people end up losing that carbon for whatever reason. Always count your carbons, okay, to make sure that the number of carbons on the left side equal the number of carbons on the right side. Law of conservation of mass, right? Well, that concludes the second part of chapter 2. This is all about how to make alcohols. And so make sure you read through this chapter. Like I said, it's a lot of review. Go back to chapter 8. Review over those reactions too, especially those alkene reactions that help us make alcohols. And practice the homework problems in the textbook. Okay? The next time you come visit the chapter 17 lecture, we're going to talk about reactions of alcohols. Okay? So just keep practicing, and I will see you next time.